All right, we're on. Okay, just a quick review of what I just did here so that we have it on film. Elvis, thank you for participating. I appreciate your support. Here's the equation for kinetic energy. The relationship between kinetic energy and velocity is a squared function. So if I put 2 here, 2 for the mass, I get 4, right? 2 squared times 2, 1/2, correct? If I double the velocity, I get 16, yes? And we know that if I double the mass, I'm going to double the kinetic energy. But if I double the velocity, I will quadruple. Please expect a question on that relationship. Very important relationship. Okay. There are a lot of squared relationships in physics. There's a lot of inverse square relationships in physics. A very common inverse square relationship is sound intensity. Sound intensity. So the intensity of sound is inversely proportionate to the square of the distance. So as the distance increases, the intensity will decrease as an inverse square function. So the sound will dissipate very quickly because the sound will travel as a ever-enlarging sphere. Understood? So there are a lot of square and inverse square functions in physics. Okay, so this is a simple machine that we'll review, okay? And the data I'm going to give you is, this is an object that has a weight of 500 newtons, all right? This plane here, the inclined plane, we'll say is DI, and we'll say that that's 40 meters, okay? We'll say that this is not necessarily drawn to scale, and we'll say that this is going to be 2 meters, okay? Not necessarily drawn to scale. All right, now, so we could say the DO now is going to be 2 meters. So you have to recognize that that's the weight, yes? You have to recognize that that is the DI, the input, what I'm actually putting in. And then you have to recognize that this is the DO, correct? You have to recognize, I'll make this a little smaller, 2 meters, okay? You have to recognize that the FO is going to be 500 newtons, because that's the weight. So that's going to be 500 newtons, okay? I'm going to apply, my force that I'm applying is going to be, let's say, I don't know, my applied force is going to be, do you have a calculator? Quick. Let me make something up quickly. Make it look halfway intelligent. So, all right, that's, all right, let's see. Okay. All right, so here, thank you. So we'll say that the applied force is going to be 40 newtons as the applied force, correct? So I want to know things like the following. I want to know IMA, I want to know AMA. I want to know efficiency. I want to know friction. Okay? Clear? What else do we want to know? Is there anything else? Is that pretty straightforward? So given a problem like this, you have to be able to identify, oh, we need Fi. Is this coming out on the video? Is it all there? Yes, perfect. Perfect. Okay, so what can we say here? Can we fill any of this in? Yes, so the weight is going to be the FO. The FA is going to be the FI, correct? So what would the ideal mechanical advantage be? Anybody? What's the ideal mechanical advantage? Remember, the ideal mechanical advantage doesn't include any kind of friction or the possibility of friction. Yes? So what do you think the ideal mechanical advantage would be calculated using? It would be something that's a constant, that doesn't change. So wouldn't it be the distances? So what is, it's going to be the larger over the smaller. So what would the mechanical advantage be of this machine? Remember, this is 40. So what's the mechanical advantage? Yes? It would be 20. Is that what you said? Okay, so that's 20. What's the actual mechanical advantage? What would it be? 12.5, is that what you said? Is that what you said? 12.5, let's see if that's correct. So it would be 500 divided by 40. What is that? 12.5? Okay. So that's 12.5. Well done, Professor. Okay? And what would the efficiency be? What would the efficiency be? What would it be? Anybody? Okay. 0.625. Try to get that answer there, Ahmad. 0.625. Now you know that could also be presented as 62.5. If I give you the efficiency as 62.5, you know that you would use 0.625, correct? Yes? Okay, so what would the amount of friction be? What would the amount of friction be? In other words, what should the Fi be under ideal conditions? We know that FO DO equals FI DI, correct? And we know that this FO is 500, and we know that's newtons and meters, so we're good. Everything's going to work out. The DO is going to be 2, and the DI is 40. So what is 500 times 2 divided by 40? What do we got? 25. 25. Okay. So Fi equals 25 newtons. All right, that's ideal. Correct? 25 newtons, correct? So what would, and I used 40 newtons, so what would my friction be? If you need a calculator, I'll be surprised. So, ideally it's 25 newtons, Miriam, correct? But I use 40. What's the friction? That's absolutely correct, Elvis. Well done. It's going to be 15 newtons. You guys are very quiet today. It's okay. All right, so easy. So given the problem, if I give you a picture, you have to be able to identify all of this. Correct? You get it? If I give you the weight, you have to know that that's the FO. If I give you an applied force, you have to know that that's the FI. You have to be able to determine the friction. What's causing the inefficiency? We didn't really talk about that, did we? But isn't that inherent in any of these problems? The friction? Clear? What's the change in potential energy? What's the change in potential energy? It's going to be mgh up here. Mg is the force, which is the weight, and then it's the height, correct? So you have to know all of this. And you did well on the quiz today, so I'm very optimistic. Understood? Yes? And let's see if that's all on the film. It looks good. Okay. Excellent.